Studio Kite, we founded in the early 90s, and we were building props and sets for theatre, and then quickly moved into the movie industry. Every month we have several jobs come through where we need to have these big objects made. We would just go through blocks of polystyrene making large sculpture. In the early days that was getting out the chainsaw and the handsaw and the rasp, and sculptors would carve that away, adding bits on as mistakes were made, and you'd dig out the polystyrene to insert steel frames so that things would be strong enough to do their job. And then in 2000, I made a small extruder that used to feed a 4mm wire. I built this in the workshop with a little motor, and we bolted that onto the big robot arm, and we started 3D printing. We were using milling software and reversing the files, but once that slicing software became open source, that was it. That was the time I knew we had to move. We had to find a new system that would move faster and be safe to work around. And this was when CADzilla's design was born. When you go big, you need to put out lots of material. We can now print sort of 8-foot high sculptures within a working day. We can pump out nearly 80 odd kilos within that day quite easily. That's what we pushed with CADzilla, was getting it to move really, really fast and accurate, and pouring out lots and lots of material. And those two things are a very difficult juggle, hence the crazy design we have with the big extruder hanging overhead, and the material is fed in through a heated line. And that meant that we weren't moving the big extruder around. That's just slowly being hoisted up above. We'd seen the 3-arm Delta machine. They're inherently a little bit shaky, this design. We needed it to be more rigid. And so we ran a bunch of calculations with an engineer, and we pretty much worked out that if we put a 4th motor on this design, we will stiffen it up 50% again. The design also then became a square, and a build area in a square is much larger than it is in a triangle. So the footprint of the machine, if it was a triangle, would have had to be much bigger to print the same size objects. It's smaller, it's easier to insulate. The 4 motors give you an error check. So if there is any one of those motors is doing something it's not told to do, the other 3 motors won't let it move. So it means you're never going to get a runaway machine. It's never going to injure somebody because it's doing something you haven't told it. We've worked in conjunction with the company that makes the software, and they've been willing to make modifications just for us because no one's doing what we're doing. Our machine uses a pellet. Most machines use filaments on a roll. We can buy our material bulk in raw form and just feed that into the machine. It's a big screw inside of a barrel, and that's got big heating elements that wrap around the outside, and the material feeds into that screw and gets pushed, and as it's pushed down, it melts with the heat. There's a new material that we've discovered that we can get very cheap, and it's chipped up HDPE, which is the white milk bottles that we're all familiar with. Councils have giant piles of this stuff. They can't get rid of it. It's just getting crushed and put into landfill. It's extremely robust in the print. And there's some furniture that we really want to produce this way. Because we have a vibrating plate that's always flattening, so we're not putting a round bead on a round bead. We're actually putting a ribbon on a ribbon. We can have that ribbon maybe 8mm wide, but only going up 1mm. So it means our overhangs can really reach out a long way. And that's another good advantage with having a robot that can move fast, put down lots of layers. Means the material can cool quicker because it's thin layers. It'll cool quicker, which means it can come back over, and you can get much finer detail. So speed is really important for details. You design so it's efficient to build. Many times the object doesn't have to have any integral strength, it just needs that outside wall. So we can just spiral those shapes up very quickly. However, in the case of it needing to be extremely strong because people are going to be jumping on it, or it's going to be hanging off the side of the building and needs to withstand wind loadings, we can print in an internal honeycomb type structure. And this stiffens it all up. It takes a little bit longer, but you end up with a much more durable object. And depending on how durable you need it, we just literally increase or decrease that infill. And different patterns can be incorporated, which are part of the look. If we use the right sort of exterior coating, it can last outside forever. And these can be water-based fillers. We don't have to use epoxies or polyesters. Whereas with the traditional polystyrene and urethane coating the Ferrari high gloss finishes is very difficult. With using the ABS, it's easy. You can sculpt in the negative form, which means you can make sure all of your clearances are correct. It's such a hard thing to do in the real world. You would have to start again. In the cases with these dogs, we can put the skull inside and sculpt the outside and the inside at the same time in the computer. This is something you couldn't do with clay. You'd be putting the clay on the outside of a skull and then inevitably having to pull the clay off and dig away the skull and put the clay back on. We can print something out, cast it, make a small change very quickly and then print another mold. We don't have to go through that whole sculpting process again. Like the furniture design and perhaps some of these big water fittings, the idea is that it may not be the ultimate way to produce lots and lots of those parts, but 3D printing will be the way to make 10 or 50 of them. Whereas if you're going to injection mold a product, you may have up to $100,000 in a big steel mold to produce just one shape. You can also just print something. If it's a kayak or a canoe, you can sit in it and go, you know, it just needs to be a little bit wider. You can put that canoe into a water testing environment so you can test the friction and what have you on the hull. And if you don't like it, that's fine, just chip it up and we'll do another one. And you can do another one in the next day. You don't have to go through this big process of making the form, coating it, digging out the form, putting it in the water. From experience, buying this sort of early tech means that if it fails, you might have months of downtime waiting for parts or advice on how to fix it. That would be, I'd say, be one of the big bonuses for somebody who wanted to purchase the machine, is they know that they're going to be talking to the people who designed and built the machine. So we can work around problems where we'll have spare parts all on hand, ready to go. We know the machine very intimately now. We knew what we needed from the machine very clearly, so we use it very regularly, which means it's been tried and tested. We've pushed it to its failure limits many times, so therefore we know how to adjust it. And a lot of the people who are trying to do this are not focusing in on that, and so therefore their machines take up to 10 times longer to print something, which is not commercially viable. It's not brain surgery. There's a process. Most people can come in and operate the machine easy. There's a lot of stuff that takes a lifetime to learn, which is the designing of the parts and the understanding of the engineering and being able to see an object in space and go, that'll work. Those skills are something that don't come overnight. The actual operation of a machine is really easy.